Welcome to the Deep Dive. Today we're digging into something really central to how databases work. Transactions.
Yep, the bedrock.
Absolutely. I mean, think about it. Whenever you buy something online, update your profile, save game progress, transactions are humming away in the background, making sure everything, stays consistent.
They're the silent guardians of data integrity.
Exactly. So our mission today is to get a really solid, deep understanding of these transactions, like really break them down, almost like we're prepping for a big exam on this stuff.
Right, covering all the bases, making sure we know how they work and how the system keeps everything reliable.
Precisely. And we've got some great material to guide us. Excerpts from DBMS M5 DeepDIVE, notes from Prof. Sarju S. for a Database Management Systems course.
Yeah, proper academic stuff, so structured, detailed, perfect for really getting into the nuts and bolts. Exactly what you'd want for that hypothetical test prep scenario.
Couldn't have said it better.
Yeah.
So what are the key study areas for today, the main things we need to master?
Well, we'll start with the core transaction processing concepts. That means concurrency control, the transaction model itself, why it's significant, the different states a transaction goes through.
Okay, the life cycle.
Exactly. And the system log, super important, plus those essential ACID properties. Everyone needs to know ACID.
Absolutely. Atomicity, consistency, isolation, durability. Gotta have those down cold.
Then we'll move into schedules.
Right.
Serial versus concurrent, the whole idea of serializability.
Ah, right. Making sure concurrent operations are still correct.
Yep. We'll look at conflict serializability, view serializability, and also recoverability, different types of schedules, and what they mean for data safety.
And finally,
A quick look at NoSQL databases, just a peek at how they handle things, kind of as a contrast.
sounds like a comprehensive plan.
Yeah.
All right, let's dive in. The absolute basic definition, what is a database transaction?
Okay, fundamentally, it's a logical unit of work. It's a sequence of database operations, could be reads, writes, inserts, deletes, that the system treats as like a single indivisible chunk.
So even if I do something simple, like, say, transfer money online, that's actually multiple steps behind the scene.
Oh, definitely. That high-level action gets broken down. Think about it. Read the source account balance, decrease it, write it back. Read the destination account balance, increase it, write that back. Those are the lower-level tasks.
Like the re-item, modify item, write item mentioned in the source.
Exactly those. And the system needs markers too, like begin transaction to signal the start, end transaction, and critically commit if it all succeeds.
Or rollback if it fails.
Precisely. Roll back if something goes wrong. It's not just the actions, but how the system manages them together as one unit.
Okay, so it's a managed sequence, and these transactions, they have a life cycle, different states they pass through. This feels very much like exam territory.
Absolutely. It starts in the active state. That's when it's actually doing those reads and writes.
Busy doing its job.
Right. Once it finishes all its operations, but before the database makes those changes permanent, it hits the partially committed state. It's like saying, okay, I think I'm done, pending final approval.
A waiting zone almost.
Sort of. If everything checks out, if the system confirms the changes can be permanently saved, then it reaches the committed state. Success. The changes are durable.
But things can go wrong, obviously. What happens then?
Yeah, failures happen. If a transaction runs into trouble, maybe a system crash, maybe it violates a database rule, maybe the user cancels it, it enters the failed state.
Okay.
And from the active state, it could also be explicitly aborted. That means any changes it did make get undone, rolled back,
Wiped clean.
essentially, yeah. And finally, whether it committed successfully or got aborted and rolled back, it ends up in the terminated state. It's finished its journey in the system.
Active, partially committed, committed, or failed, aborted, and finally terminated.
Got it.
Now, the notes really stress something called the system log. Sounds like the database's black box recorder. Why is it so vital, especially for reliability?
The system log is absolutely crucial. Think of it as the database's indestructible diary. It records every significant action a transaction takes that affects the data in chronological order.
What kind of entries does it make?
The source lists several key types. You've got start transaction, T marks when transaction T begins. Then, very importantly, write item T, X, old value, new value.
Well, okay, so it logs what transaction T, what data item X, the value before the change, old value, and the value after new value.
Exactly. That detail is critical. There's also re-addendum, TX, just knowing that T read item X, and then the final outcomes. Commit, T for success, and abort, T for failure.
Why log both the old and new values for a write? Seems like the new value is the important one if it succeeds.
Ah, but what if it doesn't succeed? That old value is essential for atomicity. If the transaction fails midway, the log tells the system exactly what the original value was, so it can perform an undo operation and roll back the change.
Right, the all or nothing part.
Precisely. And there's a golden rule mentioned. Log entries, especially for writes, are made before the actual change happens in the database itself. This is called write-ahead logging.
Log first, then write to the database.
Yes, it's fundamental for durability. If the system crashes right after a transaction commits, but before the data is physically written to disk storage, the log still has the record of the commit and the changes. When the system recovers, it uses the log to make sure all committed changes are properly reflected in the database.
That makes total sense. The log is the safety net. Okay, let's hit the big one. ACID. Atomicity, consistency, isolation, durability. These are like the commandments of reliable transactions, right?
Yeah.
The absolute must-knows for our exam prep.
They really are the gold standard. Let's break them down. First, atomicity.
The all-or-nothing rule we just touched on.
Exactly. A transaction is treated as a single, indivisible unit. Either all its operations complete successfully, or if any part fails, the entire thing is rolled back. The database state is left as if the transaction never even tried to run.
Like our bank transfer example, debiting one account, crediting another.
Perfect example. You debit account X, but before you can credit account Y, the system crashes. Without atomicity, money just vanished. Atomicity ensures that if the credit fails, the debit is undone too. All or nothing.
Okay, solid. Atomicity, indivisible. Next up, consistency. This is about keeping the database in a valid state, right? Following all the rules.
Precisely. Consistency means a transaction must transform the database from one valid state to another valid state. It must preserve all the database's defined integrity constraints, data types, unique keys, foreign keys, any specific business rules.
So back to the bank transfer. If there's a rule that the total money across all accounts must stay the same.
Consistency ensures that the amount debited equals the amount credited. The transaction maintains that overall balance rule. If only the debit happened, violating atomicity, the database would be left in an inconsistent state, breaking that rule. Consistency prevents that.
Got it. Keep the database valid according to its own rules. Now, isolation. This one always feels a bit trickier. It's about concurrent transactions not messing each other up.
That's the core idea. Isolation ensures that even when multiple transactions are running concurrently, they appear to be executing sequentially, one after the other. The intermediate state of one transaction shouldn't be visible to others until it commits.
So they don't tread on each other's toes while they're working.
Exactly. Imagine transaction T reads count X, then transaction T updates account Y, and then T reads Y. If there's no isolation, T might get the new value of Y, but based its earlier logic on the old value of X. It's working with a mixed-up snapshot of the data.
Leading to wrong calculations, potentially.
Potentially, yes. Like calculating a total sum based on inconsistent values. Good isolation mechanisms prevent one transaction from seeing the partial, uncommitted work of another. It's like they each have their own private sandbox, even though they're running simultaneously.
Okay, like invisible walls between them while they operate. Finally, durability. Once it's committed, it stays committed.
That's it. Durability guarantees that once a transaction successfully commits, its changes are permanent. They will survive subsequent system failures, crashes, power outages, you name it.
And this relies heavily on the system log again.
Absolutely. The commit record itself goes into the log, usually on stable storage. If the system crashes and restarts, it checks the log and ensures that the effects of all transactions marked as committed are properly applied to the database. Your online purchase confirmation means the order will be there when the system recovers.
ACID. Atomicity, consistency, isolation, durability. Feels like the pillars holding up database reliability. Okay, so the notes mention the significance of concurrency control and recovery. Given ACID, this seems obvious, but let's spell it out for our test prep mindset.
Sure. Concurrency control is vital because, well, real-world systems have lots of users accessing data at once. Running transactions one by one would be incredibly slow. Concurrency allows interleaving, boosting performance.
But that interleaving is where the danger lies, right?
Yeah.
Without control.
Exactly. Uncontrolled interleaving can break isolation, lead to inconsistent data, violate those ACD properties we just discussed. So, concurrency control mechanisms are the rules of the road that manage this interleaving safely, ensuring correctness while getting performance benefits.
And recovery.
Recovery is all about upholding atomicity and durability when things go wrong, like system crashes. Without good recovery mechanisms using that system log, a crash could leave transactions half-finished, violating atomicity, or lose committed changes, violating durability. So both are essential for a trustworthy database.
Which leads us perfectly into the common problems that arise without good concurrency control. The notes list a few classics. First, temporary update or dirty read. What's that?
A dirty read is when transaction T1 modifies some data but hasn't committed yet. Then transaction T2 comes along and reads that modified but still uncommitted data.
Okay.
Now, what if T1 fails and has to roll back its change? T2 has already read and potentially acted upon a value that technically never existed permanently. It read dirty data.
Ouch. Basing decisions on data that gets erased later. Bad news. What about the incorrect summary problem?
This happens when one transaction, say TSUM, is calculating an aggregate, like a sum or average, across many data items. While it's doing that, another transaction, TUPDate, is busy changing some of those very same items.
So TSUM might read some old values and some new values.
Precisely. It gets a summary based on a mishmash state that never actually existed at one single point in time. The calculated total or average is just wrong.
Like trying to count heads in a constantly shifting crowd. Okay, then there's the lost update problem. Sounds serious.
It is. Imagine T1 reads a value, say an inventory count. Then T2 also reads the same initial inventory count. T1 updates the count, maybe deducts an item sold, and writes it back. Then T2, still working with the original count it read, performs its own update, maybe deducts a different item, and writes that back.
So T2's right overwrites T1's right.
Exactly. T1's update is lost forever because T2 didn't know T1 had already changed the value. Only the last writer wins, potentially losing earlier valid updates.
Critical in many systems. Inventory, banking. And the last one mentioned is unrepeatable read.
Right. This occurs when a transaction reads a data item, does some other work, and then later reads the same data item again within the same transaction.
Okay.
But between those two reads, another transaction, T2, swooped in, modified that data item, and committed its change. So when the first transaction reads the item the second time, it gets a different value than the first time.
So the value isn't repeatable within the same transaction.
Exactly. Which can break application logic if it assumes a stable value. The notes also briefly mention phantom reads, which is similar but involves rows appearing or disappearing between reads, usually due to insertions or deletions by other transactions.
Okay, a minefield of potential issues if concurrency isn't managed. This perfectly sets up the need to understand schedules. What exactly is a schedule in this context?
A schedule, or sometimes called a history, is basically just the sequence, the order in which all the individual operations, read, write, etc., from a set of concurrent transactions are executed by the database system over time.
So it's the actual timeline of what happened when.
Pretty much. And the big distinction is between serial schedules and concurrent or non-serial schedules.
Serial sounds simple, one after another.
Exactly. In a serial schedule, all operations of transaction T1 finish completely before any operation of transaction T2 begins, then T2 finishes before T3 starts, and so on. No overlap, no interleaving, just a strict sequence.
Safe, but maybe slow.
Generally safe, yes, because each transaction sees the database as it was left by the previous one. But yeah, can be inefficient, doesn't take advantage of potential parallelism.
And concurrent schedules are where the interleaving happens. Operations from T1 and T2 might be mixed together in the timeline.
That's right. Concurrent schedules allow operations from different transactions to be interleaved. This is done to improve performance, throughput, resource utilization.
But it's also where those problems like dirty reads and lost updates can creep in if we're not careful.
Precisely. The interleaving is powerful but potentially dangerous. We get speed, but we risk incorrectness.
So we need a way to allow concurrency but guarantee correctness. This must be where serializability comes in. A concurrent schedule is okay if it's equivalent to some serial schedule.
That's the core idea. Serializability is the standard for correctness in concurrent schedules. If a concurrent schedule produces the same final database state and has the same effect on each transaction as some serial execution of those same transactions, then we say it's serializable.
We get the performance of interleaving, but the guaranteed correctness of a serial execution. Genius.
It is a cornerstone concept. Now, there are different ways to define this equivalence. The notes focus on two main types: conflict serializability and view serializability. Conflict serializability is often the first one people learn.
Okay, conflict. It
Yeah.
focuses on operations that conflict with each other.
Yes. We need to define what constitutes a conflict between operations from different transactions. There are 3 conditions, and all must be met.
Okay, lay them out for us.
1. The operations belong to different transactions, say T and TJ. 2. They access the same data item, say X. 3. At least one of the operations is a write MX.
So two reads on the same item don't conflict.
Correct. Read is fine, but read-write conflicts, write-read conflicts, and write-write conflicts. The order matters for these pairs because one can affect the result seen or left by the other.
Right. If T reads X and then TJ writes X, the order matters.
Yeah.
If they happen the other way around, T reads something different.
Exactly. So the relative order of these conflicting operations is critical.
Which leads to conflict equivalence.
Yes. 2 schedules are conflict equivalent if they involve the same set of transactions, and the order of every pair of conflicting operations is the same in both schedules. You can often swap adjacent non-conflicting operations without changing the conflict equivalence.
Okay, but how do we test if a concurrent schedule is conflict serializable? Is there a systematic way? The notes mention a precedence graph. Sounds like a key tool for our exam.
It absolutely is. The precedence graph, or conflict graph, is how we check. You create a node in the graph for each transaction involved in the schedule, T1, T2, T3, etc.
Okay, one node per transaction.
Then you draw directed edges based on conflicts. If an operation in transaction T conflicts with the later operation in transaction TJ on the same data item, you draw an edge from T to TJ.
So the edge direction follows the time order of the conflicting operations.
Precisely. Specifically, 1. If T does write X and later TJ does read X, draw T TJ2. If T does read X and later TJ does write X, draw T task TJ3. If TT does write X and later TJ does write X, draw T task G.
So we examine the entire schedule, find all pairs of conflicting operations on the same data item, and draw the corresponding edges.
Exactly. You build the whole graph representing all the conflict dependencies.
And what does this graph tell us? How do we know if the schedule is conflict serializable from the graph?
The crucial theorem is this. A schedule is conflict serializable if and only if its precedence graph contains no cycles.
No cycles, meaning you can't start at a transaction node and follow the directed edges back to where you started.
Correct. If there's a cycle, say T1 Nisel T2 Nisel T1, it means T1 must come before T2, T2 must come before T3, and T3 must come before T1 in any equivalent serial schedule. That's impossible. A cycle means there's no valid serial order that respects the conflicts in the concurrent schedule.
Okay. So no cycle means it is conflict serializable. A cycle means it's not. The examples in the notes must show this clearly.
They do. They walk through building the graph for different schedules and identifying cycles or lack thereof. For instance, seeing T3 read X after T1 wrote X creates that T1 90s T3 edge. You map out all such dependencies.
And if the graph is acyclic, no cycles, does that tell us which serial schedule it's equivalent to?
Yes, it does. If a graph is acyclic, you can perform a topological sort on the nodes, transactions. A topological sort gives you a linear ordering of the nodes such that for every edge, client TJ, Ti comes before TJ in the ordering. Any valid topological sort of the graph represents an equivalent serial schedule. There might be more than one if the graph allows multiple valid orderings.
Okay, conflict serializability. Build the graph based on conflicting operations. Check for cycles. No cycle means it's good, and a topological sort gives the equivalent serial order.
Seems clear and definitely testable.
Very much so. Now, the other type mentioned is view serializability.
Right. The notes say this is a bit broader, maybe more complex.
It is generally considered broader. Conflict serializability is a subset of view serializability. If a schedule is conflict serializable, it's guaranteed to be view serializable. But there are some schedules that are view serializable, but not conflict serializable.
Interesting. So what makes a schedule view serializable? It's about being view equivalent to a serial schedule. Exactly. And view equivalence has 3 specific conditions that must hold between the concurrent schedule, S, and some serial schedule.
Okay, condition 1.
Initial read. For every data item X, if the first transaction to read X in schedule S is T, then the first transaction to read X in the equivalent serial schedule S must also be T. They must agree on who read first.
Makes sense. Condition 2.
Updated read. This is about dependencies. If, in Schedule S, transaction TJ reads a value of X that was written by transaction T, and T was the last one to write X before TJ read it, then in Schedule S, TJ must also read the value of X written by T. The same read from relationship must hold.
So who wrote the value that you read must be the same in both schedules. Got it. Condition 3.
Final rate. For every data item X, if the transaction that performs the last write operation on X in Schedule S is TK, then the transaction that performs the last write on X in the serial Schedule S must also be TK. They must agree on who had the final say on the value.
Initial read, updated read source, and final write must all match between the concurrent schedule and some serial schedule.
Correct. If you can find a serial Schedule S that satisfies all three conditions relative to the concurrent Schedule S, then S is view serializable. The detailed example in the notes is really helpful here, walking through checking each condition.
So view serializability looks more at the overall data flow and final result rather than just the pairwise conflicts.
That's a good way to put it. It's a more relaxed condition, allowing some interleavings that conflict serializability might forbid, as long as the overall view, initial reads, read sources, final writes, matches a serial execution.
Okay, 2 types of serializability checking understood. This feels like solid ground for understanding concurrent correctness.
Yeah.
Now, the notes shift slightly to talk about recoverability of schedules. What's this about?
Recoverability deals with ensuring that we don't have situations where a transaction commits based on data from another transaction that later aborts. It's about managing commit dependencies correctly.
Avoiding commitments based on potentially phantom data.
Exactly. The basic definition of a recoverable schedule is one where if transaction TJ reads data previously written by transaction T, then T must commit before TJ commits.
So TJ can only commit after it knows the data it read from T is permanent.
Precisely. This prevents TJ from committing based on T's data, only to have T abort later. The first T1, T2 example in the notes shows this. T1 writes, T1 commits, then T2 reads and commits. That's recoverable.
So what makes a schedule irrecoverable? The second example must show the opposite.
It does. An irrecoverable schedule is one where TJ reads from T, then TJ commits before T commits. If T then subsequently aborts, we have a huge problem. TJ has committed based on data from an aborted transaction. There's no easy way to undo TJ's committed work.
Yeah, that sounds like data corruption waiting to happen.
That's-
Definitely want to avoid irrecoverable schedules. What about schedules recoverable with cascading rollback?
Okay, so these are technically recoverable. They follow the rule. Commit TJ only after T commits if TJ read from T. However, they have a potential downside. If TJ reads from T and then T aborts before committing, TJ must also be aborted.
Okay, that makes sense.
But what if another transaction, TJ, had read data written by TJ before TJ was forced to abort?
Then TJ would also have to be rolled back.
Exactly. You can get a cascade of rollbacks. One initial abort triggers potentially many others, which can be inefficient and waste a lot of processing. The third T1, T2 example illustrates this potential.
Right, like dominoes falling. Doesn't sound ideal.
Great.
Which naturally leads to the last type. Cascadeless recoverable schedules. These sound like the best option.
They generally are considered the most desirable from a practical standpoint. A schedule is cascadeless if every transaction reads only data items that were written by transactions that have already committed.
So you're never reading uncommitted, dirty data.
Never. You wait until the transaction that wrote the data has successfully committed and its changes are guaranteed to be permanent. The fourth T1, T2 example shows T2 waiting to read A until after T1 has committed.
And this avoids the cascading rollback problem.
Completely. If a transaction aborts, no other active transaction could possibly have read its data yet because it hadn't committed. So no other transaction needs to be rolled back as a consequence. It simplifies recovery significantly. That's why they're often preferred.
Recoverable, avoiding irrecoverable, and ideally cascadeless to prevent cascading aborts makes perfect sense. Wow, okay, that was a deep dive into transactions, ACID, concurrency issues, serializability, and recoverability. Feeling much more prepped for that hypothetical exam now.
It covers the core concepts of traditional relational database transaction management really well.
Absolutely. Now, as promised, the notes wrap up with a brief intro to NoSQL databases. How do these newer kinds of databases fit into this picture, or do they change the rules?
They often operate quite differently. NoSQL emerged to handle different needs: massive scale, flexible data models, high availability, often sacrificing some of the strict guarantees of traditional ASA2 transactions.
So different types exist.
Yeah, the source mentions 4 main categories as examples. Key value stores, like Redis, super simple. You
Yeah.
have a key, you have a value, great for fast lookups, caching,
Like a dictionary.
pretty much.
Yeah.
Then document databases like MongoDB. They store data in flexible JSON-like documents. Good when your data structure isn't rigidly fixed.
Schema flexibility.
Right. Then column family databases like Cassandra, they store data by columns grouped into families, optimized for huge data sets distributed across many servers, focusing on high availability and rate performance.
Built for big scale.
Definitely. And then finally, graph databases like RangoDB or Neo4j. These are all about the relationships between data points, representing data as nodes and edges. Perfect for social networks, recommendation engines, fraud detection.
So a whole different zoo of database types. How do they handle transactions and consistency compared to the ACD model we spend so much time on? Is it just different?
It's often very different, and it varies hugely even within the NoSQL world. Some might offer ACD&Ts, but maybe only for operations within a single document or single key. Many prioritize availability and partition tolerance over strict consistency, often leading to models described by the BASE acronym, basically available, soft state, eventual consistency as opposed to ACID.
Eventual consistency, meaning it'll be right eventually, but maybe not right now.
Sort of, yeah. It means that if you stop making changes, the system will eventually converge to a consistent state across all its distributed nodes, but there might be temporary inconsistencies along the way during concurrent updates. It's a trade-off. You gain scale and availability, but you lose immediate strict consistency.
Fascinating. So the strict ACD rules aren't always the primary goal in the NoSQL world. Depends on the use case.
Exactly. It depends entirely on what the application needs most. It's a whole other area ripe for its own deep dive, looking at specific NoSQL systems and their consistency models.
Definitely noted for the future. Okay, let's try and wrap this up. We've covered a huge amount of ground today. We established that transactions are the core units for maintaining database integrity.
Check. And the ACD properties, atomicity, consistency, isolation, durability are the guiding principles for making them reliable.
We saw the problems concurrency can cause dirty reads, lost updates, etc., and why we need concurrency control.
Leading us to serializability conflict and view as the benchmark for ensuring concurrent executions are correct, equivalent to some serial order.
And we looked at recoverability, understanding the importance of recoverable schedules, and why cascadeless ones are usually preferred to avoid cascading aborts.
A really solid overview of the key transaction management concepts in primarily relational systems, with a nod to the different world of NoSQL.
Absolutely. Understanding this stuff is just crucial, isn't it? Whether you're building systems, managing them, or just relying on them every day. It's about ensuring data accuracy and reliability.
Couldn't agree more. It's foundational knowledge.
So to leave our listeners with something to chew on, building on everything we've discussed, considering how complex it is to guarantee consistency with all this concurrent activity, where in the real world are those ACD properties absolutely non-negotiable? Think about specific applications or systems. And what would be the real-world fallout, the consequences, if those ACD guarantees failed in those critical situations?
That's a great question to ponder. It really connects the theory to practice. Maybe look into locking protocols or timestamp ordering, or even how specific databases, relational or NoSQL, actually implement these controls.
Plenty more to explore. Thanks for joining us on this deep dive.